Perfect. All right. Yeah, my name is Timo Löhr, and I'm working at the Technical University in Munich, and I will present our approach for the MSSEG-2 challenge here. And as you are quite familiar with the challenge now, I will directly start with the architecture. And I think I can still not, no, I can. So the architecture, so basically we transferred the challenge task into a binary segmentation task of all lesions in both time points and try to subtract the segmentation from those 2 time points in the end in order to identify only new lesions, so appearing lesions in the second scan. And our architecture is based on a 3D unit segmentation problem. And yeah, our pipeline is has basically 3 steps: the pre-processing, the unit segmentation, and the post-processing. So let's have a detailed look at those single steps. First, we are trying to align all input images. So we're doing this standard intensity normalization, some value standardization to 0 and 1, and we co-registrate all images to the MNI atlas. So we have the same resolution and the same size for all images. This is especially important because we are not only training on the challenge data, but also on external data sets. So we have to be able to compare also different patients from different data sets and enforce some similar data characteristics for an easier model training in this step. After the pre-processing, we're doing the segmentation. So as I said, it's based on a 3D unit. It's basically the standard NN unit. We have skip connections as well, instance normalization, and we use a leaky reload activation function in this case. In addition, we also use data augmentation like flipping, rotation, shearing, just to make the model more robust, especially because we also have images from different scanners here. And another important thing is maybe that we use the combination of dice and cross entropy loss as a loss function here, and we are weighting them equally. The third step is then the most interesting part in our approach, which is the post-processing. So we now have a segmentation mask of all lesions for both time points. And of course, we only want new lesions now in the second time point. So we are subtracting the segmented lesions in time point 0 from the segmented lesions in time point 1. And once they are overlapping in both time points, we are trying to remove them as they are already there in the first time point. And we're doing this by running a connected component analysis. And once they're overlapping a little bit, we are just deleting them. And in addition, we are also removing some smaller segmentation artifacts as we detected them during the segmentation, and mostly they are wrong if they are really, really small. So in the end, in the best case, we only have then new lesions included in the final segmentation masks here. So as I said, we are not only using the challenge data set here. I think you already know now how it looks like, but we are also using a second data set which was collected here at the University Hospital in Munich. And so we have around 500 patients coming from only one scanner here, but also with multiple time points, and also some medical experts segment here all the lesions in those scans, and also new lesions. So what we are doing is to train our model on the second data set first, and trying to fine tune our model weights then on the challenge data set in order to get the best model. Of course, we have a validation set, which consists of roughly 10 patients, if I remember correctly. And we pick the model based on the best die score on the validation set. And here you can see some results from our model. So top level is the prediction and bottom level is our ground truth. And as you can see, we can detect and segment the larger lesions quite good. And in some cases, we do miss smaller ones. For example, in the first one, top left is a smaller one. We do miss because those are mostly the hard lesions to catch during this task. That's it about our presentation. So come back to our poster and ask some questions. Thanks.
Thank you very much. Perfect timing. So we will go to the next presentation by Betula Sarika from ITU. Beytullah, are you there?
Yes, hello.
We can hear you, but very, very faintly.
Can you hear me right now? Very well.
Yes, but the voice
Okay.
is quite low.
How is it right now?
So and so, I would say. Can you speak a bit louder, please?
Yes, of course, but on the screen, my presentation is not there yet.
Yeah, so I've given you the control. You should be able to control my mouse and then click and move through the slides.
But I think, Olivier, I think we still see Timo's presentation. We see the experiments from Timo's presentation.
Yeah, but you can click on the presentation and
okay, perfect, perfect. Okay, so there we go.
Okay, okay. First of all, I would like to thank everyone who participated and organized this challenge. So my name is Beytullah Sarıca from Turkey, Istanbul Technical University. And in this challenge, so our presentation is new MS lesion segmentation using deep residual attention unit using the 2D slices of the 3D MRI images. Here is the content of our presentation. First, I am going to give the aim of the study and give the information about the data preparation and show you the end-to-end pipeline, give the information about the data augmentation which we used, and explain you the model which we used and some samples results into the slices. Then finally, I will explain you the 3D binary mask reconstruction. And aim of this challenge is as all we know, the MRI is widely used for the disease diagnostics, patient follow-up, monitoring therapies, which names like get more information about the MS history, and also comparing one time point to another one to find the new lesions has an important marker. And if you automate this segmentation, could also help the physicians to evaluate the patient disease. This is our motivation. And finally, so we use the encoder-decoder architecture, which use the standard unit architecture, deep residual learning, and standard attention gate to detect the lesions on the second time point using the 2D slices. We use the slice-based approach here for on the 3D MRI images. As you know, like we had a raw MRI data, so we just want to use the pre-processed one. So use the Anima script to pre-process all the training 3D MRI images to use in our pipeline. Here is the pipeline, and we just extract the slices based on the orthogonal plane orientation from each 3D MRI based on the three views, axial, coronal, and sagittal views. Then we did for this one for each time point. After that, fuse these two time points to create a two-channel input stack to the deep learning models. Then after that, use the prediction on the 2D masks. Then create a 3D mask using the majority weighting. So I will explain that next. And here is the data augmentation which we used, and we have some input values here, like we use the rotation, shift range, and shear range, and zooming, and horizontal flip, vertical flip. And here is the one sample from our training set as a data augmentation. Okay, here is the unit model, which is modified with the residual blocks with the standard attention gate. We prepare the input data with the two channel using the time from the each views, then combine them to create a one single training data set. And here is we use the 200 epochs, and with the dice and focal loss together, binary focal loss as a loss function. And yeah, this is the overview of the architecture that we used for this challenge. Here is the standard attention gate. We added this one to the this attention gate as is proposed, like between the skip connection and upsampling, to learn it more, to focus on the more shape and size. Here is the output of our learning curve and then dice score. As I said, we use the dice and binary focal loss, but we set our epoch is a 200, but the model is like to reach like more than 100, almost 100 epochs. And this is the validation and training learning curves for both dice and loose and dice score.
I really apologize to interrupt. We're already a bit above 5 minutes, so just
okay. Okay, I'm almost done. Here is the samples, the prediction samples on the 2D slices. From our model is like not get the predictive well, I think, based on this visual output. And finally, so we have the produced the 3D binary mask using the 2D slices, predicted 2D slicing using the majority voting. Yeah, I think this is the end of my presentation. Thank you for your listening and attention.
thank you very much, and apologize for interrupting. So let's move off to the Mediaire presentation. Sébastien, could you please take over?
Yes, hello. Can you hear me?
Yes.
Okay, great. Then, yeah, I can see the slides yet.
I've given you the control. You should be able to go to the next slide. We have to wait.
Okay. Yeah. Thanks. Okay. So good afternoon to everyone, and thanks for the organizers for this really interesting challenge. I'm presenting the work we contributed together with my colleagues from MICCAI, which is a company in Berlin that develops software solutions, medical, for radiologists. And our work is a triplanar unit with orientation aggregation. So yeah, I'll tell you something about the data and pre-processing we did, our model architecture, which shows for the segmentation, and some details about the training and the inference, where we did some steps to tune our model. So we actually submitted 2 pipelines. The first one just used the official challenge training data. And the second one also included additionally 25 data sets of our own. And the pre-processing, I guess, is quite standard steps. We did the registration to MICCAI template, cropping, resampling, and pixel normalization. And we split the data into 5 folds and to perform cross-validation. Okay. The model architecture, you can see an overview here, so I'll walk you through. So the pre-processed flares that we have of the 2 time points are the input, and they are sliced in all 3 orientations. So we get coronal, axial, and sagittal slices, which are then paired of the two time points. And these two channel inputs then are passed to a regular 2D unit. And then we get as output the segmentations in 2D in all three different orientations. And these are then reassembled to 3D segmentation masks, which are then aggregated in a final step. So this aggregation, I will come to that in detail at the end of the presentation. And first, some details about the training. So we used data augmentation, as you can see here. Then the updates of the model weights is done with the standard stochastic gradient descent with momentum. We used a combination of dice and top K cross entropy loss. So the dice to focus on the quality of the segmentation, and the top K cross entropy loss to focus on the hard cases and perform the F1 score and improve the F1 score. And and we trained on batches, 20 slices. Then we have the inference. So like I said, we trained 5 models in 5 folds. So at inference time, then we do a softmax averaging of the 5 models. Note that in this step, we still have the predictions for all 3 orientations. So we only average for individually for each orientation here. So I will come to the final step now, which is the final aggregation of the orientations. And here we try different strategies in order to leverage the precision and the recall. The model we chose at the end is the one that we use, has the best F1 score here, which is the most conservative approach, if you want, which only accepts lesions if they are found in all 3 orientations. We found that this was the best overall score. The other approach is more sensitive. They could improve the recall, but with the cost of lower precision. So thanks for your attention, and we hope to see you at the poster number 12 if you want, and answer your questions.
Thank you very much. The next presentation for MedICL by Hua Hong. Apologies for the pronunciation. Hua Hong, are you there? Can you please take over?
Yeah, sure. Yeah. I didn't see any control bar. Yeah, okay. Oops. Yeah, cool. Hello everyone, my name is Hua Hong Zhang. I work for Vanderbilt University, and in this presentation, I would like to show you our method for the MS New Lesion Segmentation Challenge. In general, we use a fully convolutional neural network to segment MS lesion from 2 time points. We use decade slices from 3 different orthogonal views to achieve a 2.5D method that provides both local and global information for segmentation. We also apply an augmentation strategy to make our models more robust. And finally, we use ensemble to make the final prediction from models trained with different settings. So in general, our method is based on our previous work, multiple sclerosis lesion segmentation with tiramisu and 2.5D decade slices. It achieved good results from MS lesion segmentation. especially for ESP 2015 datasets. In that work, we use a very straightforward data representation called 2.5D stacked slices, and it consists of two terminologies, 2.5D and stacked slices. As shown in this figure, a stack of 3 slices is defined as a center slice and its 2 adjacent slices. While the central slice is the most important one, the neighboring slice provides contextual information about possible lesions. A stack of adjacent slices, excuse me. So a stack of adjacent slices from any plane provides global information from 2 axes and local information from the 3rd axis. So showing this figure, the terminology 2.5D is defined as generating stacked slices along 3 orthogonal planes. In a real MRI scan, it's like taking stacked slices from axial, coronal, and sagittal planes. And the combination of 2.5D and stacked slices explores the 3D nature of MRI, but are still like secret 2D slices. See? So it's efficient. Sorry. Sorry for this. So it's efficient for chaining. It enables the network to learn the global structure from all 3 orientations. In the test phase, we just use the inference results from 3 orientations for the majority vote to output the final segmentation results. So in this method, the network we use is the tiramisu network, which is a combination of UNet and DenseNet. And this is the final network architecture we use in this work. In this figure, time point 1 is a stack of 3 slices from axial plane, and time point 2 is another stack of slices of the same position from the following time points. The network simply takes 2 time points of the samples and concat them, process them, then directly output the segmentation result from the center slice. So by doing this for each axis, we make the final prediction with majority vote. Then in this work, we use L2 loss and focal loss, which are shown to perform very well in our previous work. To get more robust MS lesion segmentation results, we use many different data orientation, and then they can be divided into 3 categories: spatial-based augmentation, quality-based augmentation, and histogram-based augmentations. And the details can be found in our short paper. For the experiments, the dataset contains 100 MS patients. 40 of them can be used for chaining. We split them into 5 folds for cross-validation, and we use AnimaScript for pre-processing. And for the evaluation during chaining process, we use the same metrics as the challenge does. So we use F1 score for lesion detection and DICE score for lesion segmentation. For the images with no new lesions, we try to reduce the number of new lesions and volumes of new lesions detected by the network. Then we have a final score that is the weighted sum of these metrics. We use this final score to determine which iteration of model we would like to use. And we use Adam optimizer. Finally, we made an ensemble of 3 different settings. The first one is using L2 loss and batch normalization. The second one uses focal loss and batch normalization. And the third one uses L2 and instance normalization. All models are trained with patches that's 3 times 192 times 192. Yeah, that's it. Thank you for listening.
Thank you very much. Perfect timing. So we'll move on to the presentation from MICCAI with Francesco.
Yes,
Francesco?
hello.
Hello.
Yeah, can you hear me well?
Perfectly.
Yeah, great. So let me try to move the slide.
I'm giving you the control.
Yeah, I saw it now. Perfect. So
It usually takes a few seconds.
yeah, it doesn't seem to be working actually.
Try to click on the part of the screen where you see the slides, and then move with the arrows.
Yeah, the arrows actually doesn't do anything.
Seems you have lost remote control. Let me try again.
Okay. Okay, yeah, great. So, hello everyone, I'm Francesco La Rosa from EPFL Switzerland, and I will briefly pitch our method for the challenge. The title of it doesn't seem to be there, but anyways, our method is titled a subtraction image-based method to detect a new MS lesion based on a single contrast flare MRI. And so contrary to most of the methods presented earlier, actually, we decided not to use a deep learning based approach, but rather go with a more classical method, which heavily relies on the subtraction image between the 2 time points. And those are some of the motivation for this choice. So first of all, the high variability of the data. Like we heard before, there are data acquired with 15 different scanners, very different pixel size and image resolution. And as well, we have pretty limited number of labeled new lesions, whereas the total lesion mask for those patients were not provided. And furthermore, previous studies in the literature have shown very promising results for detecting new lesions based simply on the subtraction image. So this is a scheme of our pipeline. We start with the images of the 2 time points, and those are then pre-processed with MSSEG, which is a tool which is part of FreeSurfer. And during this pre-processing, we have skull stripping and N4 bias correction, as well as brain parcellation. And after that, we obtain a subtraction image, simply computing a pixel-wise subtraction between the time point 2 and the time point 1. After that, we apply minimum size to all the connected component, and also a threshold to this image. And finally, we have some additional spatial constraints and radiomic features, such as the sphericity and the contrast of the lesions, which actually helped us partially at least reducing the false positive. And this is at the end our final output. So looking at some preliminary results, those are part of the training set. So on the right-hand side, we can see a table with the detection rate, the false positive rate, and the dice coefficient for the 4 experts versus the consensus mask, as well as the results obtained with MSSEG longitudinal and our proposed method. And first of all, we can tell that our method performs quite decently in terms of detection rate. We have a detection rate which is comparable to the single expert. However, we still have a quite high false positive rate. And the dice coefficient as well is still probably not satisfying. So to conclude, we can say that, first of all, our method heavily relies on MSSEG brain parcellation, which is a supervised method based on a Gaussian mixture model. And we obtained some promising detection performance on the training set. However, those have to be verified, of course, in the testing data set. We still have a quite high number of false positive, which could be perhaps later be reduced with the CNN. And this is all from my side. I'm happy to take any question or discuss together at the poster session, and I Thank you all for your attention, and special thanks to the organizing for putting this great event together. Thank you.
Thank you very much, Francesco. So yes, we'll discuss and we'll have questions in Gathered Town. Now we'll move on to the next presentation, which will be given by Jose from Neuropoly. Jose, are you there?
Hello, everyone. Can you hear me?
Hello. Yes, perfect.
Great. Right, great. So hello, everyone. I would like to first start by thanking the organizers for organizing this fascinating challenge. I'm Uzay from Team Neuropoly, Polytechnic Montreal, and welcome to our teaser. So just a couple of words about the problem at hand. The task of segmenting new lesions can help choose the best treatment early on, but visually identifying these new lesions in longitudinal data is time-consuming and error-prone. Deep learning is a promising avenue for segmentation, but many challenges remain, such as out-of-distribution generalization. So consequently, in this work, we propose a soft segmentation approach, mainly inspired by previous work in our lab for automatically detecting new MS lesions. So what exactly do we mean by soft segmentation? First of all, soft ground truths are formed from binary ground truths during pre-processing steps such as co-registration and data augmentation steps such as elastic deformation. This is mainly due to the interpolation steps involved. Most deep learning-based pipelines are trained and evaluated with binary ground truths, but this fails to capture uncertainty in voxel values, inter-expert ambiguity, and partial volume information. On the other hand, soft ground truth trained models have better calibrated outputs, and we find that normalized ReLU also works better as the final activation for these type of models as opposed to sigmoid. Here we visualize our general methodology we use for the challenge. Raw data is first passed through a pre-processing stage and data augmentations, which yields a soft ground truth that we talk about. These two sessions are then concatenated and propagated through a multi-channel modified 3D unit, and the soft ground truth is later then utilized in the loss function. To sum it all up, our methodology differs in a robust pre-processing stage with two-step co-registration, replacement of binary ground truths with soft ground truths, and using a normalized ReLU. In pre-processing, we resample images to isotropic resolution with 0.5 millimeters. We extract the spinal cord and do an initial co-registration using these spinal cord masks. We then extract brain and do a final co-registration using the joint brain spinal cord mask. Finally, we apply N4 bias field correction, and we crop both sessions such that they only include the volume of interest. The model we use, we call it modified 3D unit, and it differs from the 3D unit with the following features. First, we use smaller filter sizes to prevent overfitting. Then we use instance norm instead of batch norm for small batch sizes in 3D. We also use leaky ReLU instead of ReLU between convolutional blocks, and a normalized ReLU as the final activation, as previously mentioned. There's some lag. Olivia, maybe can you help me? Because I'm pressing. Oh, thank you. For our pipelines, the first pipeline is a modified 3D unit as previously described. Our second pipeline is an ensemble of 3D units where we have 3 modified 3D units and 1 attention 3D unit. Finally, our last pipeline is the attention 3D unit with Monte Carlo dropouts, where we use dropout during inference and average 10 Monte Carlo samples as the final output. As conclusion, for the MSSEG-2 challenge, we have a pre-processing stage with two-step co-registration and a modified 3D unit trained with a soft segmentation approach. You can find our code for this work at this given link below. And in the future work, we will focus on developing better sampling strategies to tackle the class of imbalance. Thank you for listening, and we look forward to chat with you in the poster session, and we're team 15. Thanks.
Thank you, Jose. So next presentation will be given by Berke from the New Brain team. And once again, apologies to all of you for the name pronunciation. I hope I'm not too mistaken. So Berke, are you there?
Yep, I'm here. Can you hear me well?
Yes.
Yep.
Okay. So if I click, it should move.
Yeah.
There we go. Okay. Hi. Good afternoon, everyone. I'd like to start off by first thanking the organizers for this challenge. I'm Berke Basharan, and I'm presenting on behalf of Team New Brain from Imperial College London. And our proposed method for the MSSEG-2 challenge is titled Cascaded Networks for New MS Lesion Detection. So why is this challenge and data set important? Being able to incorporate longitudinal data for lesion analysis is crucial for tracking multiple sclerosis disease progression. Furthermore, there's a huge lack in methods which allow for the temporal dimension of the disease to be included in the lesion segmentation process. And also this data set is unique as many new lesions which form happen to be small and less hyperintense on the FLAIR scan, providing a difficulty in the challenge as shown in the example here. So to solve this problem, the chunk of our method used two 3D units, the first providing a lesion probability map and the second outputting the new lesion mask. In this challenge, we also used the 2015 ISBI and the 2016 MICCAI MS lesion segmentation datasets, which provided 5 and 15 new number of additional patient data respectively. And this increased our total patient data from the 40 supplied by the MSSEG challenge to 60. A bit more detail into the method. The raw baseline and follow-up scans were pre-processed during doing brain extraction using the FSL toolbox, and the baseline was registered to the follow-up scan using affine and freeform deformation registration using the MICCAI toolbox. Normalization and imagery sampling was also done. The first unit in stage 1 was trained using the 2015 and 2016 datasets and outputted a probability map of where all the new lesions were in the where all the lesions were in the baseline and the follow-up, and the difference of these probability maps provided the probability heat map of where new lesions had formed. This heat map was the output of stage 1. Stage 2 of the method was trained using an ensemble of the provided datasets from the MSSEG-2 challenges. The input is the heat map and the pre-processed follow-up FLAIR scan, and the output of the pipeline is the segmentation mask of the new lesions. During the development of the method, the final segmentation outputs showed an overall undersegmentation of the lesions. Small lesions were either not segmented or were severely undersegmented. And to alleviate this issue, we decreased the threshold of classifying probable lesions as voxels. So normal argmaxing the output of the network means you're thresholding at 50%, but decreasing that threshold down to 10% increased the dice accuracy from 53.3 to 62.5%. And as the threshold was decreased, the sensitivity increased. However, the positive predictive value decreased due to an increase in false positive segmentations. But given the trade-off, we selected a final threshold of 10% for the pipeline. We used a 128 by 128 by 128 patches for training, however, used a tiling strategy of patches of 192 during validation and testing. And we saw that using a larger patch decreased the number of false positives which occurred in the final segmentation output. And I've provided two example segmentations here from left to right, the baseline scan, follow-up, the provided ground truth label, and the output from our method. And then in this example, case 21 achieves a dice score of 86.2%, and case 39 a score of 87.1%. And last but not least, we were also able to correctly detect lesions which were missed in the consensus segmentation. Here in case 61, we identified a lesion which was missed, and in case 90, a no new lesion patient, a new lesion which has formed in the follow-up scan. Thank you very much for listening, and thank you to the challenge organizers once again. I look forward to answering any questions you may have during the poster session, and we are poster number 16.
Thank you very much, Berke. Next presentation will be given by Brennan for the PVG team. Brennan, can you please take over?
Yes. Can you hear me?
Yes, perfectly.
Okay.
Giving you the control.
There we go. Okay. So my name is Brennan Mitchell-Pork, and I'll be presenting our work on consensus learning with multi-reader labels for segmenting and detecting new lesions. So we've already heard quite a bit about the problem, but I'll just reinforce that segmenting and detecting new lesions is an important task, with new lesions being markers of disease activity and treatment response. So our approach involves explicitly modeling the consensus process. So to do this, we use a UNet to model each expert. In other words, we have a total of we have 4 UNets, 1 UNet for every expert. So for instance, the expert 1 model that you can see in the figure on the right is trained only with the expert 1 labels. The expert 2 model is only trained with the expert 2 labels, and so on. We then cascade the predictions from the individual expert models along with the 2 input MRIs into a 5th model, which is trained using the consensus labels. So what we're trying to do here is model the consensus process. Now, each of these units utilizes film to take into account differences in image resolution, and lesion size reweighing, which involves reweighing the loss function to better balance segmentation and detection performance. I'll also mention that we only use the data that was provided, and we make use of cross-validation to optimize our hyperparameters. So now we decided not to resample to a common resolution due to the diversity of different image resolutions and the interpolation errors that would result. So instead, we tried conditioning the network using film or feature-wise linear modulation to modulate the activations of the network based on the image resolution. So practically, what this involves is feeding the resolution of a particular sample into an MLP to produce the 2 parameters, gamma R and beta R, that you can see in the equation at the bottom. And these are then used to scale and shift the normalized activations after every convolutional layer. So again, this would have the effect of conditioning the network such that images of different resolutions are handled differently by the network. And finally, for lesion size reweighing, since this task involves segmenting a range of lesion sizes, we need to consider the relationship between segmentation and detection performance. And specifically, standard loss functions will generally segment large lesions well at the expense of missing small lesions. So to account for this, we reweigh the voxels of each lesion as a function of that lesion size, with smaller lesions being weighted more heavily than larger lesions. And by doing this, we can improve small lesion detection performance. And thank you, and good luck, everyone.
Thank you very much. So we'll now move on to the presentation made by Mariam and Marius from the SCA team. Mariam, Marius?
Yes, hello.
Hello.
Giving the control to Mariam. I think it's both of you there.
Yes.
Yeah. How do we go to the next slide?
So you may have to click on the slides, and then with your keyboard, the arrows of the keyboard should be working.
Okay. it does not work.
So you first have to click on the screen where you have the slides, where you
Yes.
see the slides, and then try the arrows.
Yes, they.
Okay, there you go.
Okay. So hello everyone. We are a joint team between neurology and machine learning from the Paris Brain Institute as well as INRI at Nice. And I'm Marius, and I'm going to present the first pipeline of this team. Our approach is based on a 3D unit that is applied patchwise to the images with patches of size 32. The challenge dataset is very imbalanced, as only 1 in 20,000 voxels is positive. In this case, it is common to oversample patches containing the annotations, but when doing so, one has to choose the correct amount of oversampling. To avoid the manual selection of this hyperparameter, we used online hard example mining, where we first do a forward pass and do the backward pass only using the patches with the highest error. And we had the idea to add momentum to the unit that is used to perform the forward pass. But unfortunately, online hard example mining was worse than manual oversampling, but adding momentum seemed to be a little bit beneficial. So it's still positive. And in the end, we achieved a dice score of about 0.25. I will now pass the floor to Theodore and Mariam for the second pipeline of our team.
Okay, thank you. So for this pipeline is, as its name indicates, it is divided into subparts. First, an intensity-based ROI pre-selection, which is a synthetic approach to select potential areas of the brain, where intensities increases longitudinally. Secondly, within those patches of potential region of interest, we used convolutional neural network to segment new lesional voxels. So we shall begin by the first part. We designed the pipeline to detect areas of the brain which has to fulfill two conditions, an increasing intensity on the second time point and a geometrical a priori. After two steps of rigid and defined co-registration, bias field correction, histogram normalization between the two time points, and intensity discretizations, we divided the second MRI by the first one and kept only voxels with an intensity ratio greater than 1.15. After an opening, in order to clean the image that we obtained in here, we extracted the connected components and kept components larger than 7 cubic millimeters. These areas with different sizes but with the same resolution as native MRIs represented potential region of interest where a new lesion might appear. They were used in the latter step as patches for voxel-wise segmentation.
The previously selected patches were used to sample flares in two time points. The flare patches served as input to our CNN to perform a voxel-wise segmentation. Our CNN architecture is constituted of 8 convolutional layers without pooling and with long-term and short-term skip connections. We added to the network 3 distance maps computed from the 3 anatomical axes in patients' brain space. We observed high remaining false positive rates in infratentorial areas. This is due to their anatomical complexity and to the fact that there were few infratentorial patches in the training set. For this, we overrepresented them by imbalancing our training dataset in order to better segment the infratentorial areas. The obtained results after the inference part is as shown by the following figure: a probability map of new lesional voxels within our potential ROIs. To obtain the binarized mask of new lesions, we thresholded by keeping only voxels with higher probabilities. Thank you for your attention.
Thank you very much. So if I understand correctly, this is the end of your joint presentation, right?
Yes.
Yes.
Thank you. We will then move on to the next presentation, which will be given by Richard for the SCAN team.
Hi, can you hear me?
Yes, very well.
Great, thank you. While I wait for control, I'm controlling now, perfect. It's great to be here with you. I was also one of the teams that was competing in Athens in 2016, so I'm very happy to be back with you again. I am representing the team from the Support Center for Advanced Neuroimaging, which is a group in the University Hospital, the University of Bern. And our method is called detection of lesion change in multiple sclerosis using a cascade of 3D to 2D networks. In summary, what we did was to take an existing method, which we had already developed for segmenting lesions in single time points called DeepScan, which was recently published, which previously operated on FLAIR, T1 and T2 images. We retrained it to operate on FLAIR images only, and we used it to generate soft lesion masks of the baseline and follow-up imaging. We then took those lesion masks together with skull-stripped versions of the FLAIR imaging, resampled to 1 millimeter isovoxels, and we used those 4 images as inputs to predict new lesions in the second time point. So a little bit about the architecture which we use for lesion segmentation. It's actually not so different from one of the SEG-ResNets, which was presented by the NVIDIA group before. What we take as an input is actually a 3D, so it's rather similar to the stacks which were used in the tiramisu paper. We take 5 by 196 by 196 stacks of images. We then pass it through 2 3D convolutional blocks, and with the padding set such that what we get in the end is then a 2D feature map. That's then downsampled using max pooling just once, and then we apply a dense series of filter blocks which are dilated, and each time we go further in these blocks, the level of dilation increases. We then re-upsample these feature maps. There's one more 2D convolutional block. And then in the DeepScan model, we were predicting not only lesion masks, but also a series of auxiliary labels for neuroanatomy, for gray matter, for white matter, for subcortical structures, for brainstem, and so on. So in order to use this model for the purpose of this challenge, we first had to adapt it to work only on FLAIR images. And we did that by continuing training. This model was trained on 50 data sets which we acquired in-house. And we simply continued the training, which is described in our scientific reports paper, but randomly dropping either the T1 or the T2 or the FLAIR, so that we then have a model which is able to predict lesions from a single contrast alone. I still have control, yes. Then we standardized, we did fairly lightweight image pre-processing. We resampled to 1 millimeter isovoxels. We standardized on a per volume basis by subtracting the mean of the non-zero intensity and dividing by the standard deviation of the non-zero intensity voxels. We use a focal loss then to predict the new lesions based on the probability maps obtained from our existing model together with the FLAIR images from that were originally provided, skull stripped. Sorry, I don't seem to have. Ah, okay. I guess I underestimated how many slides I needed. I can tell you, because I remembered that I didn't report these in the slides, that over a cross validation over 4 folds, we achieved a mean dice coefficient of 0.65 on the supplied training set. So thank you very much. I look forward to seeing you in the poster sessions.
Thank you very much, Richard. The next presentation will be given by Isabella for the SEG Lesions MS team. Isabella, are you here?
I'm here.
Hello, yes, we can hear you.
Ah, good.
And I'm giving you the control. Normally you should see something.
Okay. Do you have the slides?
Yeah, the slides are afterwards, so you can just move one slide down and it should be yours.
I'm not sure if I can do that. Oh,
Yes.
yeah. Okay. So, hello everyone. I'm Isabela Medeiros, and I'm going to present our method for the challenge, the convolutional neural networks for multiple sclerosis simulation segmentation challenge. This method was developed by me and my supervisor, Marcela de Oliveira, in partnership between Brazil and Portugal. So, the objective of the challenge is to segment new lesions of multiple sclerosis in MRI. So, in order to do this, we utilize the technique of machine learning via convolutional neural networks. Our method is called CNN new lesions and takes as input 2 flash sequences in different time points, and as output, it's the segmented lesions. Our pipeline is consisted of 7 steps. From 1 to 5, it's the preprocessing steps, where the right is stripping. Then, of course, there's resliced to isotropic resolution. After that, anisotropic diffusion is used to reduce noise. Then the intensity are normalized, and finally, the images are resized to the specific shape. Those are the preprocessing steps. After that, it occurs the parts related to the segmentation of the new lesions, where the 2 images are subtracted and are used as input to the network. And then the model is trained and used to obtain this output of the new lesions. So our method is takes the preprocessed images, subtracted, and then it's used to train our model as a U-net shape with less filters and operations. So I'd like to thank for the attention to the organizers and all the institutions linked to our team.
Thank you, Isabella. So last but not least, our last presentation is given by Julia from the No Coders team.
Hello, can you hear me?
Yes.
Okay, perfect. Perfect. Okay. Yeah. Hello to everyone. Thank you for today. And I'm really glad to present our work on UMS lesion detection with convolutional neural registration networks. Yeah, my name is Julia Andresen. I work at the Institute of Medical Informatics in Lübeck, and my colleagues and I, we are the No Coders. No Coder stands for non-correspondence detectors. And this is also the main idea of our framework. So what we want to do is we take the baseline and the follow-up MRIs, and we consider new lesions that are visible in the follow-up only as image regions that are non-correspondent between the 2 time points. And to detect these non-correspondent regions, we've developed NCRNet, the non-correspondence detection and image registration network. The basic architecture of this network is 1 encoder and 2 decoders that enable the network to, at the same time, deform the baseline to match the follow-up image and to segment areas of non-correspondences between the 2 time points. Inputs for this network are the 2 MRIs, basically no pre-processing performed, only some resampling, and the subtraction image between those 2 time points. And the network is trained completely unsupervised with a masked image distance measure. So we are looking at the difference between baseline and follow-up and mask this difference with the non-correspondence output of the network, which leads the network to segment image areas where the difference between baseline and follow-up are large. To regularize those non-correspondence maps, we introduced some further terms in the loss function that favor small segmented areas and smooth boundaries of these areas. And as always in image registration, we have a further regularization term to produce a smooth deformation field. As you can see in this non-correspondence map, we have segmentations of new lesions that appear, for example, as this bright spot here in the subtraction image, but also some other non-correspondences are segmented, for example, brightness differences or some small misalignments between the two time points are also segmented in this non-correspondence map. So we need a second step in our framework, and this is again a CNN. This time it's more or less a classical UNet, but with 3 different input blocks. And these blocks get the baseline and follow-up MRIs as input again. Also, again, we use the subtraction image, but this time we use the registered subtraction image. And an additional input is the non-correspondence map. So we use the results of the NCR net as input to the second CNN. And this CNN is then trained supervised with the ground truth labels and the dice score as loss function. And yeah, the final output is then the segmentation of new lesions. So basically a refinement of the non-correspondence map such that we only get non-correspondences that are due to new lesions here. On my next slide, yeah, that is, I've brought a short overview of the method. So the first step is NCRNet. The second step then is the UNet that uses the non-correspondence detection and registration results of the first step to produce segmentations of new lesions. And the last thing we do is masking with a brain mask to remove some false positives that mainly appear in the area of the skull in our framework. Yeah, my last slide shows a short teaser on our results. So for comparison, we've trained a UNet that gets the MRIs as input as well as a subtraction image without any preceding registration or non-correspondence detection. And we could show that if we exchange this non-registered subtraction image with the registered one, that we can achieve less false positively segmented pixels. And the second finding we had was that if we input additionally the non-correspondence map, we can show a significant increase in segmentation performance. So all in all, we showed that this non-correspondence detection and registration eases the task of new lesion detection and improves the segmentation performance also. Yeah, this is the end of my talk. I would be happy to see you and talk with you in the poster session. It's poster number 23. And if you have questions after today, you can always send me an email to the address that is shown here. Yeah, thank you for your attention.